Hey everyone, this is Dr. Walker. This is video 532 called Spherical Capacitor. This video is basically just an example video where we are going to derive the capacitance of a spherical capacitor. So a spherical capacitor is a capacitor that consists of two concentric conducting spheres. Your inner sphere can be either a solid conducting sphere or a shell. And then the outer one is going to be a shell, obviously, since it has a conductor inside it. But typically the inside is going to be positive and the outside is going to be negative. So there will be a potential difference between the two spheres. And so we have a charge stored for a certain potential difference, and that will give us our capacitance that we're trying to find. So the example is basically deriving the equation. We do have two parts here. First part, find the capacitance of this spherical capacitor. If we follow the steps that we did in the previous video 531, first we find the field, then we find the potential difference, then we find the capacitance. So first, to find a field, we could use Gauss's law, just like we did in the previous example, but I think we already know that the field, right, in this region in between the two spheres, if we use Gauss's law, is due to the charge inside, and that's just the field due to a point charge, whether it's a point charge or a spherical conductor. We've seen many times that the field in this region here is going to point outwards, and it's going to look like the field due to a point charge. So I will skip Gauss's law for this one, just because we've done it many times. Keq over r squared, and the direction is r hat, right, pointing away from the charge. And then the next step is to find the potential difference. If you go back to video 525, we actually went through this exact same process when we found the potential due to a point charge. So since the field is non-uniform, right, it varies as a function of r, then we can't just say v is negative ed. We have to integrate negative integral of e dot ds, where ds is a path that you take to go from one to the other, wherever the 2 points are that you're trying to find a potential difference. And when we did this for the point charge, we saw that the dot product here just became EDR. So go back to video 525 if you need to see that again. But it just became EDR. So E is KEQ over R squared dr. And just for a quick summary, remember that when you take the dot product, you can think of as you're finding the component of ds that's parallel to E. Since E is in the R direction, then we're going to get dr here. And we're going to integrate from A to B. And just like the previous one, the negative is not going to matter. We're just trying to find the magnitude of the potential difference. So I'm going to leave it in for now, but we'll take it out later. Okay, so let's go ahead and do this integral. We're going to take out the constants, KEQ, and we're going to then have the integral of 1 over r squared dr. Let's not forget our negative here. So the integral of 1 over r squared is going to be negative 1 over r. We're going to take the limits from a to b. Let's go ahead and plug in what we get here. Now we can go ahead and cancel out these two negatives. We'll get KEQ, and then we have 1 over b minus 1 over a when we put in the limits. So that is the potential difference. And the next thing we can do is we can rewrite it just so we have a common denominator. And so if we have a common denominator of a times b, then we're going to multiply this side by A here, right, and this side by A, and then this side by B, this side by B, we can see that we get A minus B over AB. And the reason we're doing this is because we're going to find capacitance, so we need to divide by this potential difference, so it's easier if it's written like this as a fraction. Now, what I was saying about the negative before, we know that B is bigger than A. So A minus B is going to give us a negative answer here for this potential difference. And since we don't want that, we're just looking at the magnitude of the potential difference. Then to find a magnitude of the potential difference, we can just flip the A into B here so that we have a positive answer. So KEQ B minus A over AB. That is going to be the magnitude of the potential difference. This will always be a positive number. And now we're ready to find a capacitance. Capacitance is charge per voltage. So just like in the previous example, we're going to divide by V, delta V, but we're just going to multiply by the reciprocal instead. So A times B over KE Q B minus A. And now we see that the charges cancel out. And, oops, not the KE here. Let's see. The charge cancels out. So we have our final answer, and we can also write it in terms of the permittivity of free space. We know that KE is 1 over 4 pi epsilon naught. So we can rewrite the KE in the denominator as 4 pi epsilon naught in the numerator, and then A times B over B minus A. So that's going to be the capacitance of our spherical capacitor. And now we just have a quick follow-up here. Part B, if the radius of the outer sphere approaches infinity, what does the capacitance become? So I went ahead and wrote down the result that we just got. And now we want to take the limit as B, right, the outer radius, approaches infinity. So let's take a look and see what happens here. Well, if B approaches infinity and we have infinity minus A, then A is basically irrelevant. So we end up with AB over B. And now we can say, okay, well, the B's cancel out. So we're left with 4 pi epsilon naught A. And that is our result. Now, what is significant about this is that this is the capacitance of an isolated conducting sphere. You can follow the steps that we just took here when we found the capacitance. Instead of integrating from A to B, you can integrate from A to infinity to find the capacitance due to an isolated conducting sphere, and you will get this exact same result. So what is significant here is that a single isolated conducting sphere has a capacitance, and it's the same capacitance as that of two concentric spherical shells that have the outer shell has an infinitely large radius.